We're going to talk a little bit about what serverless is, and then we're going to deploy a .NET Lambda to AWS with the serverless framework. We're then going to talk about triggers and resources and how we can also use the serverless framework to deploy those kind of things, so that we've kind of got a full package of everything that we need to deploy an application through that serverless framework. We're then going to have some food and drink, and then hopefully with no further technical issues, we'll get part 2 going, where I'm going to talk about a couple of the case studies, a couple of the things that we've deployed. We're going to talk about chaos engineering, observability, cold starts, and monolithic serverless applications. That sounds a bit like it's something you wouldn't expect to see, but it's something you can hit without realizing it, as we'll talk about. And then finally deploying those serverless applications as well. So let's get the elephant in the room out of the way first. So the slide says servers. Where we're going, we don't need servers. The fact is you do need servers. It's a really bad name. If you're not comfortable with the name, just start calling it Jeff. Jeff works. The first Serverless Days conference was actually called JeffConf. So yeah, serverless doesn't mean that servers go away. It just means that we don't have to worry about managing and maintaining those servers. The next point is that serverless is the same way as Wi-Fi is wireless. And what this means is if you're on your phone and you send an email, at some point that email is going to hit a wire. It's the same with serverless. At some point your code's running on a server. So what is serverless? The most common kind of perception of serverless is functions as a service. This is essentially where we run discrete units of code, single pieces units of code that take some request and produces some output. Some of the most common functions as a service offerings out there is AWS Lambda on the left, your left, Google Cloud Functions, Azure Functions, and IBM functions as well. But there's also open source versions out there. If you like running stuff on Kubernetes, there's OpenWhisk. So you can put it on OpenWhisk, and if you've got an operations team that still like running Kubernetes and managing things on servers and all that kind of stuff, that's a really good option as well. But functions as a service is really just a small part of what building a serverless application actually is. On their own, they're pretty useless because we need all of those other services around it to make an application that is worth running. So the other side of that is actually managed services. And when I talk about managed services, we can talk about things like storage. So in AWS, we're talking about things like S3, more recently DynamoDB, messaging frameworks, so things like AWS Kinesis, SQS and SNS, and API proxies, so things like your API gateway. And there are loads of other services as well. We could even go as far as talking about platforms as a service. So if we think about Kafka, managed Kafka by Confluent Cloud, MongoDB or MongoDB Atlas, they're all services that take away you having to manage those servers, essentially. So why would we use serverless? The first thing is that it's scalable out of the box, and it scales really quickly. So again, it's something that we don't have to worry about. We don't have to worry about putting elastic load balancers in. We don't have to worry about DNS records at that front end. It's all built in and provided by the provider, so it's a concern that we don't have to think about. It's resilient, so high availability is built in. It's spread across availability zones in AWS. It'd be the same in Azure, I'm sure, and the other providers. And it's secure. And when I say secure, we don't have to patch servers anymore. Patching is, if you don't patch your servers, that's one of the biggest security risks that you actually have on those servers. And that's not to say the attack vector doesn't go away, it just changes where the responsibility lies. So we worry about security within the function itself. So that's things like, do we validate the event payload that goes in? Do they get access to the storage within that function as well? So there's a lot of security things that we pass on to the provider to manage for us. And it's cheaper. And it's cheaper because we only pay when code is being run. Data aside, it always costs to store data somewhere. That doesn't go away. I was at a conference recently, Serverless Days down in Cardiff, and I was watching a talk by Jan Kui, and he brought up this, this article that was on the Register, which says, serverless is awesome if you overlook inflated costs, dislike distributed computing, love vendor lock-in. But when he dove into it and actually spoke about where this article came from, it's from a white paper. And what they based it on was training AI models. So that was chaining functions with high memory and low latency production serving via batching. So I'm sure a lot of you in this room are pretty similar to me. We just build CRUD web applications and some business logic. So yeah, it's not cheaper if you want to build AI and prediction models in machine learning and stuff like that. But if you're running just a web application or you're doing some processing, back-end processing, then yeah, definitely cheaper. A quick analogy, I like to think about serverless and servers and all that stuff a little bit like going to the gym. So and does anybody go running here? Does anyone enjoy running? So if you think of yourself, you're the unit of code. When you go running, the cost you pay is the energy you exert and the time that you spent to do the run. You can go outside, you can run any time. That's the only time you're paying the cost of going for that run. If you pay for a gym, you're paying monthly. And whether you've gone for that run or not, you're still paying for the gym. So the gym is like your server in that scenario. And one of the really big benefits is that it reduces undifferentiated heavy lifting. So, you know, we're not having to go in and patch those servers. We're not having to configure load balancers. We're not having to worry so much about keeping our testing environments and production environments in sync. A lot of those concerns go away. And one thing, if you want to define what you're building as serverless, one great quote I saw recently, it actually boils down to cost. So you're serverless if it costs you nothing if nobody's using it. So if you're not running anything at that time, it won't cost you anything except for the data asterisks. So this is .NET North. We're here to see what serverless has for the .NET developer. So I'm going to jump into a little bit of what that looks like. So this was a result of, so the serverless framework, which we'll be talking about later, did a blog post in 2018. I think it was quite early 2018 actually, so the figures may have changed. But they basically grabbed all the usage stats for the people who are using the serverless framework. And when you look at this graph, you can see that the biggest users of serverless actually run in Node.js, and that's rather unsurprising. It's where it started. And rather sadly, .NET Core 1.0 and 2.0 combined don't even get past the next biggest, which is Go. So that's like less than 2% usage. So that could have changed, but it makes for sad reading. And I'm sure a lot of you in this room, if you've looked at it, you'll probably find that there has been a lag in the tooling that comes along with being a .NET developer and wanting to run stuff in Lambda, but it's certainly getting better. So if you want to run .NET functions, where can you do it? So there are two options at the moment. So I spoke about the other providers, Google, IBM. The only two that support .NET Core functions at the moment is AWS and Azure. Everything I talk about for the rest of this is going to be in the context of AWS. I'm sure it applies in Azure. I've not personally used Azure in any great detail, so no questions that grill me on that, please. This is quite an interesting graph, so it makes for better reading than the one we saw before. You can't really see it, that's horrendous. But basically, there's a load of lines up here. Look at these numbers at the bottom. This one here is AWS C# on .NET Core 2. And what we can see is that once you passed the dreaded cold start, the performance is actually as comparable with other runtimes, which is good. So I've just highlighted that there. I'll remove that slide for next time because it's pretty useless. So the serverless framework, quite basically, the serverless framework is really just a framework for deploying serverless applications. It's as simple as it is. With that, I will jump over to code. We'll write our first function. We'll see how that goes. Fingers crossed, I've still got Wi-Fi. I've been beset by technical issues, so let's see what happens. So the first thing I'm going to do is just show you how easy it is to create your first function. The function itself is pretty useless, but let's see, can people read that? People at the back, is that okay? Yep. So the first command I'm going to pop in is first command I'm going to pop in is this serverless create command. And basically, all we're saying is serverless create, template is AWS C#, and we're going to give the service a name. So the NN demo, serverless will go off. That creates something for us. So let's just get into that. We'll open up in code. So let's zoom this in. How is that? Everyone read that? So this has given us a few things out of the box. The first thing is the handler itself. Really, all we care about in here is the Lambda serializer at the top. That just allows AWS to pass the request and response once it gets into the container, running it underneath. We get a nice little build command and a build shell, which is just your standard .NET CLI interface, .NET restore, .NET package. And you get this serverless YAML as well. This is really basic to start with. You've got the service name we gave it. We can see it's on AWS, the runtime's .NET Core 2.1. And we can see the function itself down here. So this is the thing we care about. So this function is called hello, and the handler's just using the namespaces and the method names to get to what that function is. So I'm not going to do anything else with that part. I'm going to go to here. So I've trimmed this down a little bit over here. I'm just adding another couple of things in. So I've given it a region of EU West 1. The profile is just so I don't deploy stuff to our work AWS account by accident. Not production, of course. I don't have access to production from my laptop. And we can see that we just packaged this zip file here. So if I pop back to the command line, I'll just show you that this isn't already deployed. So if I pop serverless info in there, it'll tell me that this stack doesn't exist. I'll pop serverless deploy in, and this will just take a couple of seconds to go through. So what this is doing in the background is it's creating an S3 bucket where it's going to upload the artifacts that we want to deploy. It will upload those artifacts onto S3, and then it creates a CloudFormation file in the background, which also gets uploaded to S3, and then it creates that serverless stack in AWS for you. So we'll just give this a moment whilst it's going through. Great, we can see that's been deployed. Now we can test that function's running. So serverless invoke function hello. And what I'm doing is just passing a request, a payload in to test that function. So demo1 request.json. So there we go. So I've passed in the request that's saying hello.NET North. But at the moment, the only thing that can trigger this function is me doing it either from the command line or programmatically in another C# class or from the AWS CLI itself. So that's pretty useless as it is at that point. The next bit I want to talk about is stages and variables and the fact that functions need to be triggered. So if I just pop back to that code again very quickly, we can see here that I've got the stage hard-coded, which wouldn't be great once we get to like the CI/CD point, the bit where we actually want to deploy that function. So I can change the serverless script slightly to actually pull in a stage from the command line. So I can say it's like -- stage staging or -- stage production, and that will create duplicate stacks for us to kind of carry on through that point. We can define custom variables in our script using this custom section at the bottom. So we've got two. We've got the stage and a prefix. So the prefix allows us to create a good naming standard for the other resources that we'll introduce later. So we can see that a little bit when we introduce some of those things a bit later on. Perhaps more interesting is the handler and the events that we're triggering here. So if I just switch back very quickly, our functions become useful when they're triggered by something. So in AWS, that's probably the most mature of the serverless offering at the moment, and that's because they've got 47 different triggers that can trigger a Lambda to go and run something. So on this slide here, we've got API Gateway, Kinesis Streams, SNS, SQS, CloudWatch, DynamoDB, S3. There are many, many more. But basically when an action happens, it triggers the Lambda and we can do something off the back of that happening. So I've added an event handler here. It's HTTP. This is going to create an API gateway for us, which we can then trigger from, I'm going to do it via Postman, but you could do it from curl or a UI. So once this is done, we're going to see some extra bits. We're going to see the endpoint that's been created. And we're going to see, yeah, so we've got the endpoint here. We can see it's a post endpoint. So I'm going to copy this, pop it into Postman. And just to prove that there is code running in the background, I've changed the message to a hello again, .NET North. So I'll send that in. And there we go. So that's just taking the request and it's giving the response back. Okay. So that's better. We've made it a little bit more useful than it was before. But with a lot of web applications, we actually want to store the data that's being sent in. So we're going to talk about defining resources. So this is all the infrastructure that sits around the application and actually makes it a little bit more useful. So I'm going to pop this into DynamoDB. DynamoDB probably shouldn't be your first choice all the time, but it's great for like really simple stuff like what I'm demoing here. Let's just grab that now. I feel like I've missed one. Let me check. I have missed one, so I'll just skip straight to this. So what I've got in here is right. So what I've got in here is a few things. Let's scroll up to start with. So I've defined a new function. I've defined a function that's going to accept some feedback. It could be feedback for a talk in this instance, so I'm going to judge myself as the talk goes on. I've also defined a resource here. So I've got an AWS DynamoDB table. This is really simple. It's probably not correct, best practice and whatnot. But I've defined an attribute of comments. And I've given it a really low provision throughput just so it doesn't cost too much to keep that going. There is auto-scaling throughput for DynamoDB now, which is probably something to think about if you don't quite know the cost kind of models that you want around your DynamoDB tables. And finally, so we can write to that, we can also define IAM role statements around that. So that is basically the permissions that our function has to call into other AWS services. One thing that I would note with this is that whatever IAM role statement you put at the top of this file, it will apply to all of the functions in your serverless YAML file. So that's something to think about if you're trying to follow least privilege and that kind of stuff. That might affect how you build out these applications as well. I think there is a plugin to handle it per function, but that's just something to think about. So we'll get this deployed. I'll just prove that this table doesn't exist in Dynamo just yet. So this will be called .NET North. So you can see that's not there. So off that goes. There we go. So we can see that's been deployed now. We've got the endpoint for the feedback. If I refresh this, you can see we've got the new DynamoDB table there ready for us to pop stuff in. There's no items in there. So let's take a quick look at what that looks like. So I'm going to pop it in from the command line first. Spelled it wrong. Okay. I spelled that wrong. I'll do it from Postman. Skip to Postman. So there we go. That's gone in. I rate myself very highly. I'm not sure it'd be that high, to be honest. But if I refresh this table now, we can see that that has gone in there. So, you know, in the space of what 20 minutes, we've built up an application that takes some data, stores it into a database. We could start writing our CI scripts and have something technically running in production, if you want to call it within a day quite quickly, I think. Because we're starting really small, I think it starts to change your mindset a little bit that way. So that's it for part one. I've introduced serverless as a concept, what it is, why we should use it. We've looked at how to deploy .NET Lambdas to AWS with the serverless framework. We've looked at triggers and resources and why they're needed to kind of build up the application architecture as well. So part two, I'm going to start by just going through a couple of serverless use cases that we've built out, just to give an idea of the kind of environment that we've learned, a few of the lessons in that I'm going to be talking about for the kind of second half of the talk. We're going to touch on chaos engineering, what that is, how it applies to serverless, how we can do chaos engineering in serverless. We're going to look at observability and monitoring, some of the challenges around kind of debugging when things go wrong in serverless functions and serverless applications. Then we're going to talk about cold starts and how they are pretty horrendous in .NET, in all honesty. And then we'll look at deployment and monolithic serverless applications. So it's pretty interesting, some of the limits we hit down on that last point. So the first use case that I'll talk very quickly through is we were capturing customer requests, which required us to allow people to upload files and zip those files. And then when the request closed, we had a zip file that was ready for the agent to give back to the customer. So essentially what was happening is we've got the client on the left-hand side here. We created a request that pushed into a generic database. And what that created was basically a request that we could then start to capture these files for. We were storing all of these objects in S3, so we've got the bucket here. But what was quite cool was we used a Lambda to get a signed URL direct to the bucket, which allowed us to kind of mitigate some of the restrictions that we had saving data via the API gateway and the Lambdas. So we were going direct to the bucket. So that came via a different API gateway, gave us a signed URL. That was live for about 5 minutes, so you couldn't store that URL and then use it to kind of hack into the S3 buckets from that point on. And from that, when we uploaded the file, that came through, got to the bucket, and the interesting bit was when it actually started triggering things to happen. So we triggered onto an SNS topic. That then triggered 2 separate Lambdas. One of them zipped all of the files that we had in the folder for that particular request. And the other one updated the request in the generic database so that from the UI, the user could see each of the files that had been uploaded. So this probably, I mean, we spoke about costs earlier and being cheap, but this probably costs us less than 10 cents a month, including the SNS costs as well. And if you compared that to even a T2 micro, you know, like 10 cents a month compared to like the $20, I think that works out at there's a massive cost saving there, and including the kind of not running the servers as part of that as well. This one's similar in some ways, but a little bit different with triggering stuff from S3 again. But we've got a number of Kafka topics, which is taking data from a SQL server via the CDC stream. So kind of the top part of this is running in containers and servers. So that's not the interesting bit for this talk, although a lot of people like Kafka, and that's just as interesting too. But we put all that data gets serialized into Avro, which then gets stored in these buckets down here. When that data ends up in those buckets, we're triggering lambdas again via SNS and SQS to do some business logic on those. So that powers a few different use cases in our AO business side of the business as well, just to help them with like reporting, recognizing potential new business accounts, and basically kind of sourcing new accounts on that side as well. So even though there's just one lambda down there, this pattern here, SNS and SQS, allows us to trigger multiple different lambdas for different kind of use cases based off that data, and they're all running independently. They all scale independently as well. Yeah, so these are kind of two small snippets of much bigger systems, but I just wanted to show them just to give an idea of kind of the ecosystem we were operating in as we started to learn a few of the things that we started to learn. So I'm going to start with chaos engineering. Is anyone familiar with chaos engineering? Is anyone practicing chaos engineering? That hand nearly came up, it went down quickly. So chaos engineering is essentially about making things break on purpose so that you can understand what your failure scenarios are, how your system reacts to those failures, and whether or not it's reacting in the way that you expect it to react. There's a company called Gremlin who kind of do chaos engineering as a service, I guess is the best way to put it. But their definition is kind of, this isn't the IT definition, it's like chaos engineering is wider than just IT, but it's injecting something harmful to build an immunity. Perhaps the most famous example of chaos engineering is Chaos Monkey. So this was developed by Netflix, and this came to light, I think it was probably a good while back now. There was a massive S3 outage in US East, and Netflix was the only company that stayed running throughout this outage. And it turns out what they were doing in the background was killing machines on purpose anyway, so that they were able to respond in a way that they expected to, and everyone else had everything in one S3 bucket and were down whilst Amazon was down, which was not a great place to be. So that's the famous one. There's a whole host of other stuff that's kind of been built around this now. And perhaps one of the not so known about chaos engineering techniques is something called failure injection testing. And this is something that's really more prominent in the serverless space because we're inside the function. It's that kind of bit that we control. It's that kind of bit that we want to make sure is allowing us to respond in the way that we expect to respond. Probably two ways that help with this is injecting latency. So we've been talking about API gateway so far, so we're passing it in via the headers. But we can say, if this header's present, X latency injection with 10 seconds worth of latency that we want to inject to see what happens. We can pass that in via the headers. And the other one is injecting exceptions. So we're injecting like failure purposefully to see what will happen inside our function. So let's have a look at what that looks like. So there is a couple of things that I want to just show you in here. So the handler, as it was, I'm just going to close this down, make it a bit easier to see. So the handler's here. We've got the API gateway proxy response, which is the response we send the request coming in. And all that we're doing is we've got this class called chaos, and we're going to pass in the request headers to administer some chaos. What this looks like inside is really simple. We're just saying if headers contains exception injection, then throw new exception in injected exception. If it contains latency, then just wait around for that length of latency. So let's get this deployed and see what things actually look like whilst we do that. Here we go. Nearly forgot it again, sorry. So while that's deploying, I'll show you an example of what the request looks like going in now. So demo 4, we've got this exception.json. So this is a JSON representation of the API gateway request. You can see there's a collection of headers here, and we've just got exception injection true at this point at the bottom. The way I'm going to show you is like really manual. Netflix actually have a layer above their API gateway which injects these, so they inject like 0.5 of every request just to make sure it responds in the way that they expect. But not all of us are Netflix and have their resources, so I'm not going to inject that much latency in. Latency as well, it's similar. We've got X latency injection here. So brill, so that's deployed. Let us. So we're passing the exception one in first, and we'd expect this to come back with a 500 response. Yeah, so there we go, status code 500. The body is injected exception. I wouldn't recommend passing your exceptions back to the user normally, but for demo purposes, I figure it's fine for today. Let's have a look at what latency looks like. So we'd expect something similar, a nice response for the client to be able to do something with. So we can see it's taking a bit longer now. We can see that latency is taking effect. And we've got an error message back that we wouldn't expect to see as a client. So we can see it's Lambda's thrown an error. It's timed out after 6 seconds. So the Lambda function's actually got 6 seconds that it's able to run before it bombs out like this. We put latency of 10 seconds in. So based off our assertion that we'd handle this nicely, we can see that we're not. So we can actually go and do something about it now. So that's great. We've got, we're injecting some chaos. We're seeing exactly what might happen if we inject those kind of exceptions and stuff in. We could make it a lot more complex than what was there. That was like really simple stuff, and there's probably, if you want to share it across, you probably create a library yourself and use decorator patterns and all that kind of good stuff. But that leads us to think about how do we actually debug and see what's going on inside of our function. So debugging and observability. Observability is a big word these days. It's just kind of fancy monitoring, I think. But one of the things is with any Lambda function, not just .NET, it's actually really hard to see what is going on. So we'll start with CloudWatch. I'll show you what CloudWatch looks like. And let me see if I can find it. I probably need to refresh this. So yeah, just to start, to find the function that you care about is not great. So every time we've deployed, the first thing we're doing is creating, can everyone see that okay? Is that all right? Yeah. We're creating a number of log streams. So every time we deploy, there's a new log stream that comes through. If I click into this, we get some details in there. So we can see injected exception, injected latency at this point as well. That's not working properly, but it's really hard to kind of see exactly what's going on in there. There's not a huge amount of detail. And certainly if you're trying to debug to find the right log stream that it's in. So if your Lambda function is scaled up as usage goes up, you'll have potentially loads of these different log streams, and going in trying to find that is really difficult. So what else is out there? So what are the options with .NET to start with? So there are more options out there if you're running Node, for example. There's a host of monitoring companies springing up. Some of them are quite good, but not all of them support .NET. The options you've got are you can build your own. One way to do that is to trigger Lambdas off the logs and send it off to your Elk stack or Splunk or New Relic potentially, and then build your own dashboards around that. But that's hard work. You know, if we've picked serverless, it's because we want to build applications, not worry too much about building the monitoring platform around that as well. And there are a couple of other options as well. So these both support .NET in varying degrees. Thunder released a library. It was only 2 weeks ago. I've spoke to them a couple of times. I've used it. I'll show you how that runs a little bit in a moment. And Dashboard support it in the same way that I just described about building your own. So they pull from CloudWatch and build dashboards around that. I've not used Dashboard, so I can't say good or bad about it. But for the options out there, these two support .NET, which is a good thing. So let's take a look at what that looks like. So to support Thundra, there's a couple of things that we need to do. So demo 5. So if I go back into the handler here, the first thing is that we have to inherit from this class on the request handler. We specify proxy request and proxy response. And we just have to be a bit opinionated around the method handler itself now. So we've changed this to do handle request. And essentially what that's done is created a decorator around the handler itself. So within the serverless.yaml file, you'll see that we're still calling handle request, and then their class calls do handle request within our function itself. And that allows them to manage all the kind of pushing of stats and whatever they need into Thundra itself. So I'm going to include Thundra. So in this file, in serverless.yaml here, just a couple of things have changed. The main one being that we've passed in the Thundra API key. So this is an environment variable. This is at the top, the provider level. So any function that we put in this serverless file will have access to that environment variable. I'll show you what that looks like in the user interface in a second. So I've saved that. Serverless deploy. Let's give that a moment. So whilst that's deploying, we will get this up here. So yeah, just touching on it, you can see some metrics on here as well, but it's all, it's not super clear in all honesty. There we go. Yeah, so these are the environment variables. So these are available inside the function code itself to get and use within that code. It's a good way of kind of separating out the your environments as well. So you pass in certain environment variables depending on the environment that it's running in. And is that deployed now? Yeah, it looks like it. So I'm going to just invoke a couple of these. So this one's being hit by the cold start. So I'll pop a couple in just so we've got a little bit to look at. So I'll leave that running. So this is what Thundra looks like. Let's see if I can zoom this in. There we go. So at the top level, there's only one function on here, but you can imagine if you've got multiple functions, if we compare it to that CloudWatch screen that we had earlier, it's immediately easier to see what's going on at kind of a higher level. So I'm going to set this to the last 12 hours. We should have a few more invocations on there. So we can see the function name itself. We can see the average durations of this. So we can see on average it takes over a second. We might think, oh, over a second is not great. Why is that? And it's because we've got 7 cold starts in there. That impacts the length of time it takes to run these functions. We can see an estimation of the costs. So those 11 invocations is 0.0003 cent. So it's cost a fortune to run this demo. We can click into this and see a bit more detail as well. So we can see each individual request and what might have been happening. So if there was an error in there, so where we invoked the latency one earlier, we can see that this is timed out. We can see it was subject to a cold start. It's timed out. We've got the error. We can see the request that went in, so we've got a bit more information. We can debug a little bit easier exactly what's going on within this function. If we had logs, they'd show up here as well. I'm just waiting for the most recent one to go in, but it can take a while sometimes, which did have some logging. But you can see just like out of the box, it's a bit easier to see exactly what's going on. I can't say if it's production ready yet. Like I say, it's really new from Thundra themselves. It's been out 2 weeks. I think they're looking for feedback as much as anything at the moment. But we've at least got a company that's on the dotnet bandwagon and trying to help us, so that's good. You can also get like high-level metrics, average durations throughout the day, error counts by function as well, the types of errors that we're getting. So you get a much better high-level system view of what is happening within your serverless environments. Some of the other ones have like really nice graphs of your serverless applications. So similar to the architecture diagrams I shown at the start, they kind of map it out all for you. And when that happens, I'll be really happy because there's a lot of stuff going on in some of them. But that'll show you where, for an individual request, if there's an error, it'll show you where in the stack that error is happening. So you can really kind of drill down to where that is. So it's still a moving space. Observability, monitoring, debugging .NET Core Lambdas is still pretty difficult, but it is getting better. Okay, cold starts. So does everybody know what a cold start is before we start? No, so a cold start is it's essentially a startup cost for the first time that your function is executed. So if your function's been idle for 30 minutes or it's just been deployed, there's a few things that have to happen. One is spinning up a container. There's a container that runs under the hood, that runs on a server, so all that stuff's still there. But the first time we do it, there's a bit of a cost with that. For C#, it's really bad. So we can see on this graph, C# over here with 128 megabyte provisioned RAM available for it is up in the region of between 4 and 5 seconds just to get to the point that we're running the code. So this could potentially lead to a really bad experience for somebody who's using the system if it's a UI that they're using. It's worse if we attach it to a VPC. So if you need to access things that are private in your VPC in AWS, which is essentially a private network, I've seen this for 128 megabytes for C# be well over 30 seconds, which is horrendous. It's like really bad. So what can we do about that? What solutions have we got? There are no solutions. There are a few hacks. One is do nothing. So if you're not serving a UI or that initial latency isn't that much of a problem, just don't worry about it, I guess. That might not always be appropriate, but you can lose a lot of your life to trying to manage this stuff. You can increase memory allocation. So for the functions that we've got on the VPC, we're averaging about 1.5 gig assigned to that, so the costs go up slightly, but we're still talking like really low, like cents. But that's taken our cold start down from 30 seconds plus down to 8 seconds, I think it is. So it's still horrendous, but that's one thing you can do. You can periodically warm up the functions. This is known as the CloudWatch hack. So you trigger a Lambda from CloudWatch on a cron job, so maybe every 5 to 20 minutes. That then in turn invokes all of your other Lambdas with a special header, which basically allows you to exit before any code actually runs. It's not great, but that kind of keeps them warm. That falls down if your system scales up and it starts up another container to handle the scaling. So it's better, but still pretty bad. So we're left with a final one, which is to wait for AWS to fix it. I know it's something that they're actively working on. It's kind of trademarked 2019. So knowing AWS, that could quite happily come on the 30th of December 2019, and they've hit their target for that. So we'll see how that goes. I've already said this, but cold starts are worse when attaching to a VPC. So when you need to access those private resources. And that's because it's doing a few things under the hood. What it actually does is, within the worker itself, it needs to attach to an elastic network interface within the VPC, and it's actually the provisioning of that ENI that causes a lot of the problem, a lot of the issue with the cold starts. AWS are working on this. They're kind of pre-provisioning a remote NAT and ENI so that the function itself just points to that remote NAT, and that should dramatically increase or make better those cold starts, I should say, for .NET in particular, I think. But yeah, we're kind of beholden to the higher ups at AWS on when that actually comes or not. Okay, So before I move on, actually, I've got another quick demo, which is just how to increase that memory. So, Server 6, cold starts. This is really straightforward. We can do this per function or for the whole set of functions within it. So all it is essentially here. We just say, for this particular function, for our feedback function, set the memory size to 1.5 gig, 1504. You can see this in the UI if you go to it. Just down here, so the default is, the default used to be 128 megabyte. I'm going to zoom that in a tiny bit actually. So just there, the default used to be 128 megabyte, which is when cold starts really hit us bad and we were like, what is this? Default's a gigabyte now, so it's a little bit better on that default point. But if we deployed that, I'll skip that because it'll get deployed on the next one anyway. But we'll see that automatically increase for us as well. Okay, so building monolithic serverless applications. Now this is this came as something of a surprise to us. So we were quite happy with the fact that we chose serverless. We were deploying functions willy-nilly and creating resources, and it was all going in one big serverless.yaml file, and it was getting bigger and bigger and bigger and bigger. And then one day we got an error, which is CloudFormation has a resource limit of 200. So we'd create 200 resources in our serverless.yaml file, which was a bit crazy, let's say the least. There's certainly for management, but also working out exactly where it was we needed to change things and stuff like that. So we had to think of a few ways on how we kind of start to split out this serverless application. And one of the things we noticed was that there were, when we talk about bounded contexts in domain-driven design, we could see those bounded contexts just through the kind of API paths that we were creating. So each different request type, maybe there were common kind of endpoints that we were pinging as well. So we could see some natural boundaries from that as well. So we started to split those out into their own serverless YAML files. And what was happening was that we were getting new API gateway endpoints for each one. So that was like building out. So we had different URLs that we had to ping to get to these new services that we were creating. We also had new API keys for each of those as well. So it was becoming really difficult to manage. So we really needed to look at how we could share API keys and domain names across those serverless stacks. There's a few plugins that will help with that. I'll jump on them in a second. And another thing that really helped us was to define infrastructure in its own serverless.yaml file as well. So that's like the first thing that we deploy. So we deploy like the DynamoDB tables, SNS, SQSQs. So all of our infrastructure as code was just in one serverless file. If you prefer Terraform, you could perhaps pick Terraform for this point, but we really liked the naming convention that we got through the serverless framework. It kept everything in one kind of thing to learn. The way we shared stuff across those serverless YAML files is using CloudFormation output, so you can actually specify in your serverless.yaml file to say, okay, I've created this resource, so expose this as a variable in CloudFormation, and then you can reference that in other serverless.yaml files as well. So let's take a quick look at what that looks like. So last one. There's quite a few things going on in this one. So the first thing is up at the top, we're specifying an API key that we want to use. So we're using the prefix, the custom prefix that we specified earlier to say custom.stage -.NET North -demo. So that'll be dev or staging or production. It'll create an API key. We're also setting our function to private. So we need that API key to invoke the functions from now on. And we've got two plugins that we're installing. So we've got Serverless Domain Manager. And what that allows us to do is create subdomains on a domain name that we've registered in Route 53. And Serverless Add API Key. And this allows us to share API keys across those serverless stacks as well. Down in the bottom bit, there's a couple of things we need for those plugins to kick in and actually work. So API keys, it looks very much like the one at the top of the file. And that basically says if this key doesn't exist, create it. And if it does, let's just use it. And then with the custom domain, we've got a base path. And we've specified some domains in this environment file, which I've got here. So we can see that the URL we're going to share across stacks is devapi.netnorth.jonvines.com. And again, that associates it with a stage as well. And if it doesn't exist, it'll create that as well. So let's save this. Last deployment of the night. There we go. So we can see that the domain name's been registered. We've got an API key up here that we can use. I'll drop into Postman and just show this very quickly. Headers, API key, and send. So we can see the domain name that we've got up here. Last one, few, done. So that's how we can share those resources. We can deploy multiple stacks. The issue then came with deployments. So this is the last bit now. So the problem we had now was that we were doing this serverless deploy multiple times in our script, and we were changing resources that weren't always changing. So that kind of goes against the point of doing serverless. You want individually deployable units. The good thing about deployments with serverless is that it's really simple. So we've got the serverless YAML file, we've got the code, we package it, we deploy, we test it, we deploy, and we're into production, so it's super quick. But what we found was with multiple we had up to 8 at one point, and that took us from a deploy time of less than 2 minutes to nearly 10 minutes. It's not that bad in reality, but it was bad enough. So how did we handle that? The first thing we tried to do was to kind of map the MD5 hash of the package that was built, but that's different every time you actually build it, so that didn't work. So what we actually used was the git diff to look at where in the deployment code might have changed, and if it hadn't changed since the last check-in, we didn't deploy it. So for that to work, you've got to really be on kind of continuous delivery models, to get your commit into production as quickly as possible. But that was, again, it's a little bit of a hack, but it's helped us with holding multiple server stacks in one repository. So that's everything. So we spoke about serverless, we spoke about deploying them, we spoke about some case studies and a few of the problems and lessons that we've learned along the way. That is everything from me. Well, I'll be around for a little bit longer, so come and grab me if you want to chat. Thank you very much.
Thank you.